This video will briefly introduce the fundamental concepts of SfmCAD. The conventional CAD production process involves converting a collection of parametric parts into a unified shape, while reverse engineering converts this unified shape back into multiple parametric parts. In this work, our input consists of 3D voxels, which can be either whole-shape voxels or segmented voxels. Our approach aims to output a CAD reconstruction of the 3D shape, including the path and sketch for each individual component. Several deep learning-based methods have attempted to address the reconstruction task using sketch and extrusion. A common limitation of these methods is their focus solely on learning sketch and extrusion operations, without the capability to handle more intricate CAD modeling processes. Notably, ExtrudeNet and CAD utilize unsupervised methods, as do we. This choice is driven by the absence of publicly available datasets that include CAD modeling sequences beyond simple sketch and extrusion operations. On this page, we present 4 fundamental CAD modeling operations: extrude, loft, sweep, and revolve. The loft operation involves 2 distinct sketches, whereas the sweep and revolve operations incorporate paths with nonlinear segments. Next, we will sequentially introduce how our method enables neural networks to learn these operations. The extrude operation extends a 2D sketch along a perpendicular axis to create a 3D object. It involves a fixed 2D sketch and an extrusion height. For the sketch component, because it remains constant during extrusion, we train the network to learn an implicit 2D sketch representation. For the extrusion component, we simply learn the extrusion height. The loft operation creates a 3D object by connecting the top and bottom 2D sketches. Since the top and bottom sketches are different, we train the network to learn each sketch separately. For the path component, similar to the extrude operation, we simply learn the height. For sweep and revolve operations, the sketch remains consistent, similar to the extrude operation. However, the path is no longer a straight line. Therefore, we train the network to learn the control points of a Bezier curve to represent the curved path. To enable unsupervised learning of the path, we propose a pathbox representation as shown in the figure. The network first learns this rough reconstruction, and after learning the path, it then learns the actual sketch. The pipeline of SfmCAD consists of 2 stages. In the first stage, the network's goal is to learn the paths of various parts of the shape. For the input voxels, the network learns the control points of the paths and the parameters of the pathbox. In the second stage, utilizing the paths learned in the first stage, the network continues to learn the implicit 2D sketches of each component, ultimately achieving the final reconstructed output. Here we present some visual results, including those from the ABC dataset and the ShapeNet dataset. Here, we present the test results on the synthetic tree dataset and the PartNet dataset. Note that for the PartNet tests, the input consists of segmented voxels. Finally, we demonstrate the editability of the outputs generated by SfmCAD. For the network's output, we can delete specific components and modify the paths of certain parts. Additionally, we can alter the sketches of components to adjust local geometric details while maintaining the overall structure. We can also modify the twisting angles of components. Lastly, we can apply Boolean operations to create holes in the components. Thank you.